All right, folks, welcome back. We're going to look at completing this exercise that's part of, I'm just going to point out here, Unit 3, Part C, the very last exercise in the structures playground is what we're looking at today. All right, so I'm going to read the description and then I'm going to start pulling stuff over from the solution, by the way, to drop in here. And then hopefully you guys will follow along. You may have done this differently, and that's quite okay, as long as it works basically along the same lines. It says, when you worked through the types playground, you had a chance to think of some real world examples of types and the associated types they might depend on. A training shoe type, for example, might have a size property that's an int, a brand name that's a string, and a release date that's a date. Think of another real world object and its properties, make up some actions or behaviors that the object might be able to perform, and write them in plain English in a comment first. All right. And the thing that we're going to kind of work on here, real frankly, they're kind of using like the shoe example, right? As you go down here, and I'm looking at both the teacher version at the same time I'm talking to you guys, so I apologize if I feel like I'm kind of jumping around a little bit. But as you look at the examples, I just want to make sure that I'm following an example that makes sense. So what the author is doing is they're thinking of basically a structure called a computer. That's what they're focusing on. And so if you think of a computer and its capabilities, man, there's a whole bunch of things that we can make properties and functions and behaviors and all that stuff. It's a really good natural fit. So here at the top, they're asking, add your English language description of the type here. Make sure to add comment marks before each line so that we realize that it's a comment. So what I'm going to do is I'm just going to drop in all these comments at once, and then we'll talk through them. And I think that's probably the most efficient way to do this. So here they come. If it is of benefit, here it comes in the chat as well. That's just to give us a little bit of efficiency here, I guess. All right, so let's take a look at this. So they're defining basically a computer structure. Screen size will be a property. That's going to be a double. The total RAM in megabytes as an integer. Is on, which is a Boolean state, like is it turned on, for example. Who the manufacturer is a string. When it was built, a date. Turn on, which is a function, right? So if you think about the is on and turn on, that might be helpful. And then open, and in this case, a particular program as a function, right? So this is kind of the ideation of the author. All right, so now they're giving us the breakdown here a little bit. And it says, use the struct syntax from this lesson and create a type for your real world object with the properties and methods you thought of, remembering to mark each property with let or var, depending on whether or not it will be allowed to change. If you're not sure how to implement the body in one of the methods, describe what the method should do in a comment. Okay, so, and this is really actually a helpful programming technique. So if you're like building stuff, that you might not think of it as kind of like a pseudocoding technique, but it kind of is, right? You can kind of build stuff in code, drop in comments so you remember what you were trying to do, because this is what happens, right? Like we have a week since we've been together. And oh my God, we just had a hard time figuring out which exercise we were doing, which shows us all how much we were working on it in the week in between, which is basically not at all, right? And no harm, no foul, right? Because we're doing it all in class here. But yeah, man, that's a really good technique, right? And I have that problem too. Like if I'm working on code, and code can be very complex. And what I kind of tend to do as a programmer often is if I get into a flow and I feel like I'm really being productive and hitting on the code right, and, all that, if at all possible, I keep trying to flow on it, like maybe push off a meeting or skip the dog walk for the moment or whatever it is, just to keep that flow, right? And I think that's kind of what they're pointing out here. I have a little hint. It says, if you made any properties with custom types, you can create placeholder types that have empty implementations. And they say, see the training shoe code at the bottom of this page for an example. So let's go take a look at, the placeholder type. So here, right, they have, shoelaces as a structure, but notice that is, empty, right? Then they have a structure for a training shoe. Let's just look at how they're doing it. They have a size. Okay, the size seems logical that it won't change, right? Like you buy a size 12 and it's going to be a size 12, right? It's not going to become something else. Is the shoe tied, true or false? That could change, right? It doesn't take much for laces to loosen up. And then laces seem to be of type laces. So this is really kind of an interesting line here, because what this is really pointing to is that this is a struct. And how do we like normally in this spot after a colon, we would see the data type. And this is actually very telling, by the way, because once you've created a structure, in essence, it becomes a custom data type that we can refer to in all of its properties and methods and actions and behaviors and all that, right? So I think that's really interesting. So really, this variable of laces really points out this structure. They have a function called squeak. And so here's the placeholder. Make a loud noise like rubber squealing on the gym floor. All right, okay, eventually. Warn about the laces. If the laces are untied, print a reminder to tie them, right? So somebody doesn't fall on their face. But this is what they're talking about. So like, we do have a placeholder type here, in the sense, and here's comments in place of the standard code that would go there. But as a reminder, hey, we want to do this, right? And then we have the spot for it. Down below, we create an instance of shoelaces, right? And then we use the instance of the placeholder type to create an instance of your new type. Okay, that's kind of really out there. But training shoe has its, data properties here, like the size, right? Is it tied? And then the laces, which laces are we putting in here? The new laces. We don't even know what compromises that. But in principle, because it's treated as a data type, in order to create a training shoe that has those data fields, right? We do need that piece of information to make it complete. That's the general kind of overview here. So now what they want us to do is build our own structure. And because we do want this to do a couple of things, I'm going to be adding something to this, by the way, in order for our code to basically work. And I'm following, once again, the techniques done by the author already. Not that I would necessarily proceed exactly in this fashion, but it's, I think, good to know what they're intending. They do have a note here. Let's read the note. It says, if you make a method that tries to change a property of your struct, you'll see the cannot assign property to self is a mutable error, right? And what this means basically is structs have special rules about methods to try to change the values of their properties. To get rid of the error, use the keyword mutating in your method declaration. So mutating func my method that changes the property. This is really kind of an interesting thing. Kind of interesting that they drop it here, right? But I'm going to show you how they're applying it, and then it'll make sense. And what we're going to apply it to is basically the capability, like when we looked up here, kind of like as a pseudocode version of what we're about to create. The fact that you're turning a computer on or off, right, and changing its power state is pretty significant. So that'll have to be a mutating function is really kind of the grand point. Let's start to build it. And I think that this will help. So now, because we're going to be doing some pulling in from external libraries here, I'm going to import Foundation, which gives us access to a couple of things that we otherwise wouldn't have, right? Often when we have done program builds before and Foundation was used, and I'm just going to use like the Boogie Bot as an example, right? Like this is in the background. You don't normally see it declared, but I'm putting it in. The author has it in, which implies we're using some tool from this, by the way. Then I'm going to use the struct keyword, and I'm going to create a structure called computer. Turn my curlies, put a little space in there. And then I'm going to keep my eye on the stuff that I have up above here because, hey, you know what? This is not exactly code, but it's really close, right? And I can use that as a guide to build my code, including the names, the data types, and all that. So let's start with the screen size. Let's say let screen size be, it is not pre-assigned, of course, right? But we're just creating a placeholder for it. And that, if you're comparing it to the shoe, is kind of like the shoe size, right? It's like, hey, your screen's 13 inches or 15 inches or whatever. And that's just what it is, you know, and it's like, it's not like you're going to rip it off the machine and put on a new screen that's bigger. It's not going to fit. And that's actually one of the things I'm fixing on my wife's laptop right now. She needs a new screen. The current one is working, but it is not optimal, is the polite way to say it. All right, let's move on to the next one, which is total RAM in megabytes. Now let's have a discussion about this. Now, if I buy a Mac, right, a modern Mac, well, that's a let, right, for a modern Mac. If you guys don't know this, right, so like if you buy a laptop Mac, right, you're not changing the RAM on it. They're not allowing that anymore. One of the reasons, by the way, like if you see old, especially MacBook Pros, and I forget what the cutoff year is, like 2015 or 16 or something, like anything before then, man, you can open that up, change the hard drive, change the RAM, change, you know, all the stuff and fix it. And then they're like, nah, you guys can't do that anymore. So if it was a Mac, this next thing would definitely be a let. But for a PC or a desktop Mac, it might be a variable. So the total RAM, yeah, megabytes. And actually, that's kind of interesting. Did you guys know, why we use a capital B for megabytes?
No.
Yeah, there's actually a reason for it, and this is kind of interesting. So whenever you see like internet speeds reported, right? Usually you see a lowercase b, capital M, mega, and then B, when it's lowercase, symbolizes bits, which is
Ah,
1/8 of a byte, right? And then when you see a capital B, so like when you see like an internet speed, and they, of course, the cable company or the phone company will say megabits. You get 300 megabits internet service. Then if you get up on Steam and you're downloading a game is a really good example. And you're looking at your download rate and you're like, wait, Time Warner told me I have 100 megabits, but I'm getting 10 megabytes per second, and that's about 100 megabits, right? See the correlation there. This is an interesting little side bit. The other one, which is this thing turned on? That's definitely a variable because, like, computers can be turned off, right? So is on is a Boolean. True or false? Is it on? Or off? The manufacturer is going to be a given, right? So let's manufacturer. I got to spell that right. And that'll be a string. Like whoever made it is the person, is the company that made it. So that's not going to change. And then also the manufacturer date. So that's going to be actually a date field. And I think, okay, so now that I think about it, that's why we have the foundation, because some foundation won't feed in a system date, or like a date in its date format won't put it in without the foundation library. So that makes sense to me. The next thing that we would do is we would start creating the stuff that goes inside of it. So let's take a look at, so we took care right now of these things. So we have a struct, and then we added all those properties, right? And now we need to create basically, looks like two functions. One is to turn it on, and one is to open a program. All right, so let's take these one at a time, and we'll do the first one first. And so I'm going to create a func called turn on. And why am I calling it that? Because I determined that above, basically, if you're wondering. Of course, we need parentheses after it because it is a function, and we need curlies. All right. Now, I'm going to go ahead and code through this with the intent of generating an error message, by the way. So I'm going to basically do a message here, a print statement. And I'm going to say in the print statement, computer is powering on, and dot dot dot, something like that. And then we're going to switch the Boolean value of is on to true. Okay, that's good. It's all powered up. Now here is where we start to see the error message. So then we go back to what we saw above, and it says so structs have rules about try to change the values of their properties, right? So we're trying to change the value of the Boolean is on. So that means we are going to be mutating this particular property. So we need to put the mutating keyword here in front of this function. And make sure I spell that right. No, that's not a U. Right, there we go. Mutating func. Now you see the error message go away. So you see why I did that kind of backwards? Because like normally you just create a func and you're not thinking about it. But that way, if you're inside of a structure and you're creating one and you get that error message, just throw the mutating keyword in front of it and you're okay. Just really simple little Band-Aid fix. All right. The next one that we have to create is this open function where we're going to throw in a string. So like basically, which program are you opening? Xcode, pages or whatever. And that will be a function also. So let's create that down here. Once again, here comes the func keyword. And then we will say open. Just follow the same syntax from above. We'll have a localized variable called program that's in the form of a string. And here come the curlies. And okay, so now you might not think about this too much, because if you're going to open a program, you might just say a message like, hey, we're opening the program, Xcode. We're opening the Xcode program, for example. However, can you do that if the computer is turned off?
No.
The answer, of course, is no, right? So logically, we probably want to ask an if here, and we want to say if is on. Now, because this is a Boolean, is on is a Boolean, I don't have to say less than, greater than, whatever. That's either true or false. So if it's true, it runs. If not, well, we can have an else. So here comes the true state. So we'll do print, and then we'll just say which program we're running. So we'll do something like opening. I'm going to do string interpolation here. Program. Opening the Xcode program, for example. All right. If the computer's not turned on, go back up there here, my keyboard, we'll do an else, and we'll just give them a little error message. Hey, you can't do that, basically. But we'll say print. And how about computer needs to be on before you can open, and then we can just give the name of the program again. So just to acknowledge that the data was received, basically. And you know what? I call it the, Catholic college in me. I always have to finish my sentences. Lest some nun comes by with a yardstick and corrects me. All right. So there's our our completed structure. We have our properties added. Some are variables, some are constants. We have a mutating function to be able to turn the machine on. And I think it's interesting we don't have one to turn it off, but hey, whatever. Eventually the battery will run out or something. And then we also have the function open a program. And you know what? I'm following once again the author's example. Now, in order to go ahead and create one of these, okay, so that becomes like a whole separate process in itself, right? So now that we've done this, let's go ahead and create an instance of this structure. And part of this exercise really is to get the feel of how Xcode helps you create it. You know, so like how when you're actually employing it for real. So we'll use this space down here to do that. So we'll do it right in this spot here. And I'm gonna, let's say, create a variable. And okay, so let's talk about that for a second. Why am I creating a variable instead of a constant? Okay, so
Because you have to have something to call this.
well, that's part of it. But if I, think about this, if I'm creating an inanimate object, does it really need to be changing?
No.
No.
Well, okay, so yeah, well, actually, but we have stuff inside of it that changes. So, and there's your answer, right? If stuff inside of it is possible to change, if I make this a let, whatever I feed into it is always going to be that. It can never change. So in other words, I'm saying I can never turn it on and off, and I can never change the RAM, is what it would say. But I want it to be a variable because I do have aspects of it that can change, and I might want to change, real frankly. All right. So now I'm just creating an empty variable structure here. I am going to call the computer structure, put in my parens here, and then notice how it automatically IntelliSenses all the features of that structure. It reads it from the page. It's pulling in all the properties automatically. Now it's going to prompt me when I press enter to fill it all out. And I think this is really, really slick, right? So the screen size, I'm going to go, well, I'm on a 13-inch, so I don't know what that is. We'll just go 13.1, for example. Maybe that's what it is. I'm going to press my tab key. My total RAM on this in megabytes. Now, this is a whole lot different than gigabytes, right? So we think gigs, right, for computer memory. Now, if you're on a 16 gig machine, like I am right now, this is 16,384. If you were on an 8 gig machine, it'd be, roughly half that amount. But the multiplier is 1024, by the way. It doesn't really matter what number you put in here, by the way, if you're doing this, but you can just copy mine. Is the computer on? I'm going to say false. So it's just sitting there. Okay. Who made this? Well, I'm pretty sure Apple made this. And actually, do you know who manufactures a lot of Apple's products?
Foxconn.
Yeah, Foxconn does a lot of them. And they're having a lot of problems over in China right now, from what I understand. Now, the manufacture date is like a whole different thing, right? Because here, it's like, what date do I put in? And I could actually extrapolate a date. Now, they have this really bizarre thing, and I want to show you what the author has in place here, because I think this is really a fascinating little thing. So I'm copy pasting this, by the way, and here I'll put it in the chat too, so you guys can do the same if you want. But there is a way to invoke this, and I think this is a really fascinating little piece of kind of like information and computer history all at the same time, right? So we are using the manufacture date. Now, it sure doesn't like that. I'm not really sure why, but am I missing? Oh, yeah, I know what I did wrong. All right, so this should say date, and I didn't get that part of it, basically. So the manufacture date is date, and what this is, I want you to notice, I'm feeding this particular property with a function. So this is a function call. When I call date, it reaches into the system clock and extracts the date in some electronic format and the time and time zones and all that stuff. But if you notice what they did here, and I'll get this little chat window out of the way, is it says time interval since 1970. That's an interesting date. Why 1970 and not 1999? And then it's 1,300,000, or is that 1,387,584,000? Okay, so first of all, what the heck is this? What is this? Seconds, minutes, speculate. All right, here's the IT geek in me coming out. All right, I'm gonna pull up my calculator, which of course is over here. Let's take a look at the calculator and let's type that number in. All right, so 1,387,584. I'm going to speculate this is seconds, right? And is that all of it? No, there's 3 zeros in there too. All right, there we go. All right, if I divide this by 60, so I'll just use my mouse to do this here. Let's divide by 60. That would give me minutes, right? See, I'm speculating here. And if I divide it again by 60, that gives me what? Hours. And then if I divide that by 24, that gives me
Days.
days. So we're getting there. You can see the math here, right? And then we divide by 365 roughly, gives me 44. How many years past 1970 are we? It's almost 50 years, but 44 years is
Yeah.
here, right? And that would make the computer be built when? Yeah. All right. You know what? Irrelevant. All right. So let's just say it's irrelevant. Okay. The point is, you know, what they're trying to point out is if I take 1970, add 44 years to it. So what year does that become?
Oh God, 2014.
Correct. That is correct, right? So 2014. And you know that's kind of an old computer, really, right? So 2014 is really what we mean to have in this spot. I find this is a really interesting piece of information. And if you guys aren't aware of, like, why do computer clocks often, and this is more true on Windows machines, by the way, like you reset it and the BIOS gets wiped and you put new batteries in, whatever, and then it asks you to reset the date and the default date goes back to 1970. And here's the why for that. Prior to that date, there really were no computers in this kind of format that we operate today, meaning with a keyboard and a screen. There were computers before that date, but most of them did not have those features. And that's really kind of weird to think about. Wow, computer without a keyboard and a computer without a screen. What good is it, right? Yeah, they use different methods for input and output. Eventually all computers got to that. But 1970 is also when like the Unix operating system took a foothold, and actually started earlier than that. It's also when the internet took a foothold, and it's also when we didn't have really quite personal computers yet, but we had computers more in the format in what we're familiar with today, which is with a keyboard and a screen and all this kind of features that we want. So we think of 1970 as like the ground zero date for computing in the modern era. Pretty weird, right?
Mhm.
And because, you know, the computers of that era were pretty useless, you know, for the most part compared to what we have now. All right. But more importantly, we had all the concepts of everything that we're doing today were already firmly in place back then, by the way. All right. So we put in all the features. Yes, we could have just hard coded a date in. This is really kind of more of an interesting lecture point, honestly, than anything else. All right. Now we do have the MacBook now created, and now I'm going to turn it on. So here comes the turn on command. So I'm going to say MacBook dot Oh, why is it indenting like that? Well, I just figured something out. Because I opened up my paren here.
No, we didn't close it.
Yeah, I didn't close it. So Xcode kept indenting me going, hey, you're not done. So now I am, and now I'm going to turn on my MacBook. So I'm going to go MacBook dot. Notice how turn on is an option there. And that command will turn it on. MacBook turn on. All right. Next, I wanted to run a program. So I'm going to say MacBook open the program I want to open. And, Xcode is probably a good one. So let's just do Xcode. And so this is like proof of concept. And the fact that we are using internal functions and setting all the properties. All right. How do you know that it's working? Well, we have no error messages, and the console is showing the output from those functions. Right. So we know the computer is powering on and opening the program. Now, interestingly, if I remove this, and maybe not remove, let's comment it out. Now I should get, it's not an error message. This is from our code. It says the computer needs to be turned on before you can open Xcode. So that proves that this else is kicking in down here. Oh, you guys are not seeing that. I apologize.
It's okay.
Yeah, wrong screen. Right. So yeah, let's do that on this screen. So if I turn that off, notice how the message changes now because the machine's not on. Now we get the else. So we checked if it's on, we'll run the program. If not, let's throw this error message up on the screen. So it's not really an error message. It's not like a compiler error. It's just very simply a logic error generated from our code. If we allow the machine to be turned on, then we get the alternate output. Now, if we were really building a computer system or a model of a computer system or whatever, we'd also have a way to turn it off. We'd also have a way to close the program, et cetera, et cetera, et cetera, right? And think of all those pieces. Okay, so that, folks, is the solution for that exercise at the end there of that chapter. If you want to call it a chapter, I guess. And hopefully you picked up a couple of things from this, and helped to reinforce what we learned last week. We are going to be moving now into a new topic. I am going to create a new video here, by the way. So I'm going to stop this video. So this video ends here.